Hi folks, we're now looking at number 17 from page 107. So we're looking for the limit of this function here as x approaches 1. So first thing to notice, as usual, is the denominator, and we see that it is approaching 0. So that means we have to now check the numerator. So if we let x equals 1, we have 1 plus, this is just 0 minus 1, so 1 minus 1, 0. So we have an indeterminate form, meaning we have to do some investigation to see whether this limit exists or not. So this, again, I hope people really are paying attention when I make this comment. Anytime you have to deal with a limit, and we'll see even in other circumstances, when you have to operate with an expression that has an absolute value, the way to do that is to write it as a piecewise function. Okay, so luckily here, even though we have two absolute value terms, they both have the same input of x minus 1, meaning this changes from negative to positive at x equals 1. So that's where we have to split our two branches. Okay, so I'll call this expression here f at x. Okay, and I'm going to rewrite this as a piecewise function. Okay, so the first thing I'm going to do is I'm going to take the interval where x is less than 1, meaning when the expression inside the absolute value is negative. Okay, so that means that this is going to become x plus negative x minus 1 over, and this again will become negative x minus 1. So this is if x is less than 1. Okay, and now we'll take the interval where x is greater than 1. That is when this expression here is positive. So the absolute value will just end up giving me x minus 1. So here we have x squared plus x minus 1 over x minus 1. This is for when x is greater than 1. Now, of course, I'm not defining it when x is equal to 1 since it is undefined. Okay, and now here we'll simplify this. Okay, so we have x squared minus x. Okay, and then here I've got positive 1 minus 1, so 0, so just equal to x squared minus x when x is less than 1. And then here we've got x squared plus x. And then here we've got negative 1 minus 1, so minus 2. And that's for x greater than 1. Oh, let's not forget we have the x minus 1s here negative and here positive in the denominator. And now it looks like I can simplify this even more. Okay, because here this just, I factor out the x, so I'm left with x minus 1 over negative x minus 1. And then here I can do some factoring. This just gives me x minus 1, x plus 2. Okay, all over x minus 1. And then finally, okay, these cancel out. I'm just left with negative x when x is less than 1. And here I'm left with, once these cancel out, just x plus 2 when x is greater than 1. So now, when I want to determine these one-sided limits, since this function is defined differently to the left and right of 1, so I can't determine the limit directly, I have to determine the one-sided limits. Okay, so our first goal is to see whether these one-sided limits are equal or not, because if they're not, we're done. Okay, so here, when I want to determine the limit of this function as x approaches 1 from the left, I'm going to be using this expression. So that's going to be of negative x. And so here this limit, since that's a continuous function, we can just plug in the 1, gives us negative 1. But when I take the limit as x approaches 1 from the right, I now need to use this expression here, since that's the expression when the x values are to the right of 1. So here x plus 2, and we get 1 plus 2 is 3. And so here, since these are not equal, we can say that the limit does not exist. Okay, so again, just to recap, anytime you have to deal with a function that has an absolute value term and you have to do some kind of operations, you really have to first write the function in piecewise form and simplify it as much as possible. Now they ask us to graph this thing, so I'm not actually going to do it by hand, but we'll just take a look at the graph, and Desmos does this very nicely. And we see here, as expected, at x equals 1, it does not have a limit. It approaches -1 from the left, and it approaches +3 from the right, just like we found. Okay, that's it for this one here.